Hello all, welcome to the 10.3 video part 1, which we're going to be talking about the natural base, which is the base of e in logarithms. And then in the next video, you're going to be doing applications or word problems of exponents and logs. And so we first want to understand where the base e came from. And to do that, I would like to remind you that something in the past that you've talked about is something called compound interest. And compound interest is how many months or how many weeks you put money into a bank over time, and it helps calculate a loan usually. And the equation for that was A equals P times 1 plus R over N to the NT. We will actually be using this equation a lot more in the second video too, but the reason it applies now is because mathematician Jacob Bernoulli, let me spell that right. This mathematician, Jacob Bernoulli, was calculating compound interest over time with this equation. He started probably with how much money would I make if I put money in there for a week, or if I put money in for a couple weeks, or a month, or a year, or a couple years, or going up to 100 years. And then he asked, what if I put money in there infinitely, or until all time? And so again, it's amazing what mathematicians really could do, that they would take formulas and take things they already knew and recognize patterns and figure something else out. It's really, really amazing. So what he did was he took this compound interest formula and he simplified it a little bit. And he wrote it as just 1 plus 1 over n to the n power. So it looks similar to this idea, but he simplified it. And he said, if I would like to put money in infinitely, what if I found the limit as x goes to infinity? In order to understand this, what he did was he plugged in bigger and bigger numbers for n. So we started off and said, okay, what if n just equaled 1? He took 1 plus 1 over 1 to the 1 power, which would be 1 plus 1 to the first, which was just 2. Then he said, okay, keep understanding infinity. What if I said if n equals 10? So that would be 1 plus 1 over 10 to the 10th power. So this would really be 11 tenths if you got a common denominator to the 10th power. If you plug that into your calculator, you would get 2.593. So it looks like we're still in the 2 range. So to continue getting closer to infinity, Jacob then said, let me plug in n equals 100. That'd be 1 plus 1 over 100 to the 100th power, which again, if you get a common denominator, would really be 101 over 100 to the 100th power, which ended up, if you plug that into the calculator, to be 2.7048. And he continued this and he continued this and noticed a pattern. He tried n equals 1,000, he tried n equals 10,000, and he noticed that if he plugged in bigger and bigger in numbers, this limit eventually converged, and that's a word you'll hear quite a bit in calculus. It converged on the number 2.718 and kept going and going. The bigger and bigger the numbers got, it noticed that the pattern 2.718, the numbers kept coming out as that final value. And this number is what mathematicians define as the number e. Just like pi is 3.14 and continuing on, e is really equal to 2.718 and so on, and that's the number that's programmed into your calculator. And so that is how the number e was discovered, and that's why we can use it with logarithms, and it's called the natural base. So let's use this natural base and kind of figure out where these buttons are in our calculator. So you want to evaluate for x equals 2 both of these functions. So we'd like to find f of 2, so every time we see an x, we want to plug in 2. So we're really trying to find e squared plus 1. Now, e squared really means that 2.7 squared, so we definitely want to use our calculator for this. And the reason we have 2 different examples here is to show you 2 different buttons on the calculator. So if we turn this guy on, if we would like to type in e squared, right above the ln button, there's an e to the x. So you'd press second ln, and you type in squared, close the parenthesis, plus 1, and your answer as a decimal would be 389. And I'm going to put about because we rounded. You also keep your answer exact. That's perfectly fine on a test as well, but this is just to help use your calculator. For the second one, if I'd like to do g of 2, that's negative 3e to the 2 times 2 minus 3, which is really negative 3e to the 4 minus 3 power, which is really just negative 3e to the first, which could just be written as negative 3e. So an exact answer, negative 3e, is perfectly fine. But the reason that I put this example on these notes was to show you a difference. If you would like to raise e to a power, the best way to get to the e is second ln. So let me write a note here. I did second, and then I press the ln button. But on the calculator, if you'd like to just find e without to a power, that's above the division sign. So you could do negative 3, and then just do second division, and you just get negative 3e. So it would be negative 8.54. And so that would be negative 8.155, about. And so to get to this one, you would just press second and then the division sign. Both are handy. Both are used for different purposes. Now, just like the last video when we were doing log base 10, a lot of the same rules apply for the natural base or the ln. So if you're given the natural exponential function e to the x power, you can also write this as a logarithm. So you're thinking of it as base to the power equals a value. So the base is e, the power or the exponent is still x, just like the last video, and it still equals y. Now you might notice that there's two notations here. We have log base e and we have ln. These are interchangeable. Instead of saying log base 10, you could say log base e, but I will let you know that this is a much more popular notation. That in your calculator you have an ln button, you do not have a log base e. So you're going to hear me say ln a lot more, especially when we're dealing with the natural base of e. So here's the properties of the natural log. You might notice that this looks very familiar to our last video. What this means is when you see ln, you can assume that the base is really e. And remember, ln are still logs, and logs are still really exponents. So when you're looking at this, your answer needs to be an exponent. So you can think of it as e to the what equals 1. Well, any base to the 0th power always gives you the answer of 1. So this, just like log base 10, is 0. This example, you could rewrite it as when you see ln, you're assuming the base is e. So ln of e, and your value is e, and you're trying to find the exponent that makes that true. So if you think backwards or change this into an exponent in your head, e to the what equals e. Well, e to the first equals e, so my exponent, or my ln, or my log, is 1. This example, you assume there's a little e here, so you're saying e to the what equals e to the x. Well, it has to make sense that e to the x is equal to e to the x. So my exponent is x in this case. You again could think of ln and e because you have ln base e of e to the x. These things right here are inverses, exponential and logs. They technically cancel out, which is why your answer is x. In the same way, when you have e to the ln of x, these are inverses of each other, so the answer is also x, just like log base 10. And lastly, also just like log base 10, if you have the natural log of x equals the natural log of y, you're really saying ln e of x equal to ln e of y. They have the same base on both sides, which means that the arguments here, or the values, must be equal. So x equals y. Lastly, let's do a few conversions with the natural log. So if you had to rewrite this as an exponential equation, the base is really e. Again, you can write this as ln e of 4 equals 1.386294, and so on. So if I wanted to write this as an exponential, base to my power must equal my argument or my value. If you don't believe me, feel free to type e to the 1.386294 into your calculator. The result should be 4. If I change this one to an exponential, again, this really says log base e, or ln of e, 5/8 equals negative 0.470036. So the base, if I'm changing this to an exponential, the base is e, the exponent is negative 0.470036, and so on, because logs are exponents, and that should be equal to 5/8. Again, if you don't believe me, feel free to type the e to the negative 0.470036 into the calculator, and the final result should be 5/8. If we went the other direction and wanted to change the exponential into log or ln equations, or log base e, because my base is e, I know, here's what I could do first. I could say this is log base e, because I see the base, and then I know that my exponent is negative 4, so I know this needs to equal negative 4 because logs are exponents, which means that the argument, or the value, would go here, 0.0183156. Got a little squish there. Now, instead of writing log base e, it's more common just to write ln of 0.0183156 equals negative 4. There's my conversion into a log. The second example, you could think of it again as log base e, because there's my base. I know that the exponent is 3/4, so that means that the 2.117000 should be next to the log. Again, I can rewrite log base e as ln. So ln of 2.117000 equals the exponent of 3/4. And that would be your final answer. So in conclusion, log base e has a lot of the same rules, or all the same rules, as log base 10. So we'll be practicing them together very soon. So this ends the first video. On the next video, we'll be doing applications of exponents and logs. Thank you.